Hello friends, welcome to my lecture on Taylor series. Suppose Fz is equal to sigma n equal to 0 to infinity Cn z minus z naught to the power n mod of z minus z naught less than r. That means the power series converges in the region mod of z minus z naught less than r. Now we know that a power series with a non-zero radius of convergence represents an analytic function within its circle of convergence. So the question, now the natural question is, if we are given an analytic function f in some domain D, then can be represented by a power series. So our next theorem answers this question. This is called Taylor's theorem. Let Fz be analytic in a domain D and let z equal to z naught be any point in D. So let us consider any domain D, okay, and let us take a point z naught in the domain D, okay. Then Fz can be uniquely represented by the power series Fz equal to sigma n equal to 0 to infinity Fn z naught. This is Fn z naught means nth derivative of Fz at z equal to z naught over n factorial into z minus z naught to the power n. Now this representation of Fz is valid in the largest open disk with center at z naught contained in D. That is, the radius of convergence or the radius of this disk will be the distance of the point z naught from the nearest point on the boundary of D. Let C be a circle with center at z naught and lying entirely within the domain D. So let us consider a circle with center at z naught. Okay. So let us consider a circle, say this circle is C. With center at z naught lying entirely within the domain D. Now we consider any point z belonging to C, belonging to the interior of C. Okay. So for any point z belonging to the interior of C, by Cauchy integral formula Fz is equal to 1 over 2 pi I integral over C Fs ds over S minus z. Okay. Any the value of the function f at any point interior to the circle C can be found by Cauchy integral formula, and it is given by Fz equal to 1 over 2 pi I integral over C Fs over S minus z ds. Then Fz can be expressed as 1 over 2 pi I integral over C Fs over S minus z naught 1 over 1 minus z minus z naught over S minus z naught. So 1 over S minus z, okay. I can write it as 1 over S minus z naught minus z minus z naught, okay. Then I can write it as 1 over S minus z naught 1 minus z minus z naught divided by S minus z naught, okay. So Fs over S minus z is written as Fs over S minus z naught into 1 over 1 minus z minus z naught over S minus z naught ds. Now we know that 1 plus q square and so on q to the power n plus 1 over 1 minus q, okay, is equal to 1 over 1 minus q. We know that 1 plus q square and so on q to the power n minus 1. This is equal to 1 minus q to the power n upon if you take here n up to n, if you take 1 plus q square and so on q to the power n, if you take, then this there are n plus 1 terms, 1 minus q to the power n plus 1 upon 1 minus q. So I can write it as 1 plus q square and so on q to the power n plus q to the power n plus 1 upon 1 minus q equal to 1 over 1 minus q. So this is equal to q to the power n here, okay. So so from this formula we are writing 1 plus q square and so on q to the power n plus q to the power n plus 1 over 1 minus q equal to 1 over 1 minus q using from this formula, okay. So this is q, okay, this is q. So 1 over 1 minus q is equal to 1 plus q square q to the power n and then q to the power n plus 1. So q to the power n plus 1 means z minus z naught over S minus z naught to the power n plus 1, okay, and then 1 minus q, okay. So, q to the power n over 1 minus q. So, we have q to the power n plus 1 upon 1 minus q means z minus z naught over s minus z naught raised to the power n plus 1 and 1 over 1 minus q. Q is equal to z minus z naught upon s minus z naught. So, what it is z minus z naught to the power n plus 1 s into s minus z naught divided by s minus z naught to the power n plus 1, okay, s minus z naught to the power n plus 1 into s minus z into s minus z. So, this s minus z naught will cancel with 1 s minus z naught here, and we will get z minus z naught to the power n plus 1 in upon s minus z into s minus z naught to the power n, okay. So, this is this term, okay. This term is q to the power n plus 1 divided by 1 minus q, q to the power n plus 1 divided by 1 minus q, where q is equal to z minus z naught over s minus z naught, okay. So, this is how we have written this this equation. Now, when you put this value, okay, by value of 1 over 1 minus z naught over s minus z naught using this equation gives us f z equal to 1 over 2 pi I integral over c f s over s minus z naught. This term corresponds to this one, okay. Then z minus z naught over 2 pi I, z minus z naught over 2 pi I integral over c f s over s minus z naught whole square ds, then z minus z naught whole square by 2 pi I integral over c f s ds over s minus z naught to the power 3 and so on. Now, the term corresponding to this. So, z minus z naught to the power n by 2 pi I integral over c f s ds over s minus z naught to the power n plus 1, and then the last term z minus z naught to the power n plus 1 by 2 pi I integral over c f s over s minus z naught to the power n plus 1 ds, okay. Now, using Cauchy integral formula for derivatives, we have the Cauchy integral formula. Let us recall that f n z naught is equal to n factorial divided by 2 pi I integral over c f s ds over s minus z naught to the power n plus 1, where n takes values 1, 2, 3 and so on, okay. And f z naught is equal to 1 over 2 pi I integral over c f s ds over s minus z naught, okay. So, using those formulas, okay, the first term, okay, this one is f z naught, this is f prime z naught over 1 factorial, this is f double prime z naught over 2 factorial, this is f n z naught over n factorial, okay. So, we can write this equation as f z equal to f z naught plus f prime z naught over 1 factorial z minus z naught, f double prime z naught over 2 factorial z minus z naught square, then nth derivative of f z at z naught over n factorial z minus z naught to the power n plus r n z. R n z is the remainder of the series after these n plus 1 terms. So, r n z is z minus z naught to the power n plus 1, this expression is r n z. So, this is z minus z naught to the power n plus 1 over 2 pi I integral over c f s ds over s minus z into s minus z naught to the power n plus 1. Now, this equation is called the Taylor's formula with remainder r n z, okay. Now, we shall show that this r n z, the remainder of the series after n plus 1 terms goes to 0 as n goes to infinity. Since now we are given that f z is analytic in the domain D. So, since f is analytic in the domain D and the circle C lies within D, okay. So, f z is analytic on C and therefore, mod of f z assumes its maximum value. Let us take that maximum value to be m on the contour C. Okay. So, mod of f z say m is equal to maximum value of mod of f z, where z belongs to C. Okay. So, furthermore, z is inside C. Okay. You can see z is inside C. So, mod of z minus z naught is less than r. Okay. This z is inside C and the radius of C is r. Okay. So, mod of z minus z naught is less than r. Okay. R is the radius of the circle. So, in addition, since z is inside C, mod of z minus z naught is less than r, and so mod of s minus z must be greater than or equal to r minus d. Now, let us see how we get this. S minus z is equal to s minus z naught minus z minus z naught. Okay. So, mod of s minus z is equal to mod of this, which is greater than or equal to mod of s minus z naught minus mod of z minus z naught. Okay. So, d is your mod of z minus z naught. Okay. And mod of s minus z naught, mod of s minus z naught is equal to r, because s varies along the circle C. Okay. This s is the variable of integration. Okay. And the integration is along the curve C. Okay. So, and the radius of the circle is r. So, mod of s minus z naught is the center of the circle. So, mod of s minus z naught is equal to r. So, this is r minus d. Okay. D is the distance of z from the center z naught. Now, so mod of r and z. Okay. Mod of r and z, let us find. Mod of r and z is equal to mod of z minus z naught to the power n plus 1 divided by 2 pi and then mod of integral over C f s ds divided by s minus z into s minus z naught raised to the power n plus 1. Okay. Yes. So, let us see integrand mod of f s over s minus z into s minus z naught to the power n plus 1. This is less than or equal to mod of f s is less than or equal to m, because m is the maximum value of mod of f z along the curve C, and mod of s minus z is greater than or equal to r minus d. So, this is less than or equal to m by r minus d, and mod of s minus z naught is equal to r. So, r to the power n plus 1. Okay. So, this integrand is less than or equal to m by r minus d into r to the power n plus 1, and the length of the curve C is equal to 2 pi r. So, this is equal less than or equal to mod of z minus z naught. Mod of z minus z naught is d. Okay. So, d to the power n plus 1 over 2 pi into 2 pi r, which is the length of the circle C. Okay, into m divided by r minus d into r to the power n plus 1. Okay. So, this cancels with this, and what we get is m into r. So, this is m into r divided by r minus d. Okay. Then d by r to the power n plus 1. Now, d is less than r. Okay. D is the distance between z and z naught. Okay. Z lies to the interior of C. Okay. And z naught is the center of C. So, definitely r is bigger than mod of z minus z naught. Okay. That is d is less than r, and so d by r is less than 1, and therefore, d by r to the power n plus 1 goes to 0 as n goes to infinity, and we thus conclude that mod of r and z goes to 0 as n goes to infinity, and hence r and z goes to 0 as n goes to infinity for all z which lie inside C. Now, let us apply the identity theorem of the power series. So, by the identity theorem of the power series, the representation of f z in the form 2. Okay. in this form. Okay, in the form 2 is unique in the sense that 2 is the only power series with center at z naught, which represent the given function f z. Since f z is analytic in D, the radius r will be at least as large as the distance of z naught from the nearest point on the boundary of D. We can increase the radius of this circle C as long as we do not cross the boundary of D. Okay. That means, this r can at most be the distance of z naught from the nearest point on the boundary of D. If we take it to be more than that, more than the distance of z naught from the, if we cross the boundary of D, then the series may no longer represent f z at all points of D, which lie in the interior of the circle of convergence. Every analytic function has derivatives of all order. We know that every analytic function, we have seen by the Cauchy integral formula for higher order derivatives, that every analytic function has derivatives of all orders, and now we have seen that it can be represented by a power series of the form 2. Okay, power series of the form 2. Now, this is not true in general for real functions. For example, if you consider f x equal to e to the power minus 1 by x square, when x is not 0 and f 0 equal to 0, then we can see that f dash 0, f equal to 0, f double dash 0 equal to 0, and so on, f n 0 equal to 0 for all n. Okay. So, f x equal to e to power minus 1 by x square when x is not 0 and f 0 equal to 0 has derivatives of all orders at x equal to 0, but it cannot be represented by the power series about x equal to 0. If you write the power series about x equal to 0, what it will be? Power series about x equal to 0 will be is f 0 plus x times f dash 0 x square by 2 factorial f double dash 0 and so on. Okay. Now, we know that here f 0 is equal to 0, f dash 0 equal to 0, f double dash 0 equal to 0. So, power series becomes 0. Okay. So, it definitely does not represent f x equal to e to the power minus 1 by x square. So, this function cannot be represented by a power series about x equal to 0. So, this result holds in the case of complex analytic functions only. Now, every power series with a non-zero radius of convergence. Now, if you have any power series whose radius of convergence is non-zero, then it is the Taylor series of the function represented by that power series. Let us prove this. So, let the power series sigma n equal to 0 to infinity c n z minus z naught to the power n have a non-zero radius of convergence, say given by r. Then it represents some analytic function, we know. Let us take that analytic function to be f z, and say the region of convergence is mod of z minus z naught less than r, then f z is equal to sigma n equal c n equal to 0 to infinity c n z minus z naught to the power n. Now, we can term by term differentiate this series. So, f prime z is equal to c 1 plus 2 c 2 z minus z naught and so on, and more generally nth derivative of f z is n factorial into c n plus n plus 1 factorial into c n plus 1 into z minus z naught and so on. Now, all these series converge, okay, and have the same radius of convergence r. That means, they all converge in the region mod of z minus z naught less than r and represent analytic functions. Hence, these functions are continuous at z equal to z naught, and therefore, f z naught is equal to c naught, okay, f z naught will be equal to c naught, f prime z naught will be equal to c 1, and f n z naught will be equal to n factorial into c n. Okay. Or we can say c naught is equal to f z naught, c 1 equal to f prime z naught over 1 factorial, c n equal to f n z naught over n factorial, and thus we get f z equal to sigma n equal to 0 to infinity f n z naught over n factorial z minus z naught to the power n, which is the Taylor series of the function f z. Okay. So, this proves the theorem that is, any power series with a non-zero radius of convergence is the Taylor series of that function, Taylor series of the function represented by that power series. Okay, now, let us consider the function f z equal to 1 over 1 minus z. Okay. So, here 1 over 1 minus z, we can see this function is analytic for all z except z equal to 1. Let us find its Taylor series expansion about z equal to 0. So that means we f 0 we have to find f 0 equal to 1, and if you find f prime z is equal to minus 1 upon 1 minus z whole square into minus 1. So, 1 upon 1 minus z whole square. Okay. F double prime z, let us find, it is minus 2 1 minus z to the power minus 3 into minus 1. So, 2 upon 1 minus z whole cube. If you find f triple prime z, it will come out to be 2 into 3 1 minus z to the power minus 4. So, this means 3 factorial divided by 1 minus z to the power 4. Okay. In general, so this can be written as 2 factorial divided by 1 minus z to the power 3, and here it can be written as 1 factorial divided by 1 minus z whole square. In general, f n z, okay, is equal to n factorial divided by 1 minus z to the power n plus 1. So, this is valid for n equal to 1, 2, 3 and so on. Okay. Now, this implies that f n 0 is equal to n factorial, okay, n equal to 1, 2, 3 and so on, right. So, now, so the Taylor series with center at z equal to 0 is given by sigma n equal to 0 to infinity f n 0 by n factorial z to the power n, which is equal to sigma n equal to 0 to infinity f n 0 is n factorial. So, n factorial divided by n factorial z to the power n. We get summation n equal to 0 to infinity z to the power n. Okay. So, the Taylor series of the function f z equal to 1 over 1 minus z is equal to sigma n equal to 0 to infinity z to the power n, and we know that this series converges in the region mod of z less than 1, okay, and the sum of the series is 1 over 1 minus z. So, 1 over 1 minus z is equal to sigma n equal to 0 to infinity z to the power n. Now, we can see that if you take z equal to 1, okay, if we take z equal to 1, then z equal to 1 is a singularity of the function f z. Singularity of the function means the function ceases to be analytic at z equal to 1, or f z is not analytic at z equal to 1. So, f z is singular at z equal to 1, and z equal to 1 lies on the circle of convergence here. This is your, this mod z equal to 1, okay, and z equal to 1 lies here. Okay. So, the series converges for all z which lie to the interior of mod z equal to 1. So, 1 over 1 minus z is equal to sigma. This is, so sigma n equal to 0 to infinity z to the power n is the Maclaurin series of 1 over 1 minus z, and the region of convergence is mod z less than 1. Now, if you take the series 1 over 1 plus z, okay, suppose let consider now f z equal to 1 over 1 plus z. Then the Taylor series for this function f z can be found from the Taylor series of f z equal to 1 over 1 minus z. How we can do that? This can be written as 1 over 1 minus z. Okay. So, this is equal to 1 over 1 minus zeta, where zeta is equal to minus z. Okay. Now, the series the function 1 over 1 minus zeta, okay, in the zeta plane, this is sigma n equal to 0 to infinity, this is zeta to the power n, okay, where mod of zeta is less than 1, okay, in the zeta plane. in the zeta plane 1 over 1 minus zeta equal to sigma n equal to 0 to infinity zeta to the power n, where mod of zeta is less than 1. So, using the transformation zeta equal to minus z now, okay, then 1 over 1 plus z is equal to sigma n equal to 0 to infinity mod of minus z to the power n, and mod of zeta is equal to mod of minus z less than 1. Okay. So, I can say that this is summation n equal to 0 to infinity minus z to the power n mod of z less than 1. So, this is also equal to sigma n equal to 0 to infinity minus 1 to the power n z to the power n mod of z less than 1. So, 1 over 1 plus z, okay, this is the Maclaurin series expansion of 1 over 1 plus z can be found out from the Taylor series expansion of the function f z equal to 1 over 1 minus z by making use of the transformation zeta equal to minus z. Now, if you take one more function, say f z equal to 1 over 1 plus z square, okay, 1 over 1 plus z square, okay, then here also let us take zeta to be equal to z square. Okay. Let us take zeta to be equal to z square, then f z is equal to 1 over 1 plus zeta, okay, which is equal to, by making use of this expression, okay, this is sigma n equal to 0 to infinity minus 1 to the power n zeta to the power n, where mod of zeta is less than 1. We have just now seen 1 over 1 plus z can be written as sigma n equal to 0 to infinity minus 1 to the power n z to the power n mod of z less than 1. So, using this we can write 1 over 1 plus zeta equal to sigma n equal to 0 to infinity minus 1 to the power n zeta to the power n mod of zeta less than 1. Now, let us use zeta equal to z square. So, we shall write sigma n equal to 0 to infinity minus 1 to the power n and z square to the power n, and then mod of z square less than 1, okay, or we can say f z equal to 1 over 1 plus z square is given by sigma n equal to 0 to infinity minus 1 to the power n z to the power 2n, okay, and mod of z less than 1, because mod of z square less than 1 means mod of z square equal to mod of z into mod of z less than 1, which implies that mod of z square is less than 1 and which implies mod of z is less than 1. Okay. So, the Maclaurin series expansion of 1 over 1 plus z square can also be found without determining the values of the derivatives of f z at z equal to 0. We can make use of the Maclaurin series expansion of 1 over 1 plus z for this purpose and use the transformation zeta equal to z square. So, when we want to find the Taylor series expansion of a given function, we use alternate methods to determine the Taylor series expansion of the function of z. Usually we do not have to find the derivatives of f z at z equal to 0. We can make use of the Taylor series for the function 1 over 1 minus z in the region mod of z less than 1, or 1 over 1 plus z in the region mod of z less than 1, and the given function is then broken into various terms by using the partial fractions, and then we use the known Taylor series expansions for the function f z equal to 1 over 1 minus z and 1 over 1 plus z. So, with that we can find the Taylor series expansion of a given function without determining the derivatives of the function at various points, because that is there are infinitely many terms. So, we can only find the derivatives for a finite number of terms, but by using the expansions of 1 over 1 minus z and 1 over 1 plus z, we can write the entire series Taylor series for the given function. So, in the next lecture we shall discuss LoRa series, and in the case of LoRa series, because here in the case of the function Taylor series the function f z is assumed to be analytic in the neighborhood of the point z naught, in some neighborhood of the point z naught, but in practically in applications we always do not have this situation. We have to expand the function around those points where the function is not analytic. So, in that in those cases we make use of the Laura series. So, that we will discuss in our next lecture. Thank you very much for your attention.